Fun project with a lot of people taking on what is clearly an absurdly difficult problem. And it's one of those things, if you ever think of this problem by yourself, you say, I must be mad to even try this. But then you see 19 other people and there is this delusion that happens by each of us saying, if they're thinking it's doable, maybe it is, let's do it. And the other guys are thinking the same thing. So somehow we got into it and we took a shot at it. And I think we had some interesting successes to talk about. So just to review, there were many things that were done. So think about, for example, the idea that Lucas presented in the beginning, saying that you could always discover acoustic units bottom up from the signal by just saying, can I segment the signal in such a way that two segments with the same label have similar acoustics? And that's a reasonable learning problem, and that has been looked at already in the past. But then he injected this new idea into it about saying these little acoustic units that we come up with, if you want to think about them as phonemes, every language has to have some phonotactics. So there is some underlying phone language model for this language. We don't know it, but in the standard Bayesian way, we can put a prior on all possible phone n-gram models. In his case, it's a hierarchical Pittman-Ure language model, and he incorporates that into acoustic unit discovery, and indeed that ends up giving him a little bit of an improvement in the acoustic unit discovery itself. So that's a good sign, saying that injecting some kind of top-down knowledge, even if it's simple, is going to improve what kind of acoustic units you discover. In the same way, the work that Leda did said that if you do have other languages and you know nothing about the phone set of this language, so if you can't go after this cross-lingual or multilingual phone set, for example, at least you can go after acoustic features which do phone discrimination in multiple languages at once. These are the multilingual bottleneck features, and use those as your features for acoustic unit discovery and hope that therefore you'll discover more accurate acoustic units because your features themselves are good for discriminating between sounds in multiple languages. So that was another win by showing that the multilingual bottlenecks, for example, improved the normalized mutual information from something like 0.28 to 0.36 or something. So that was a nice big improvement. So ideas about borrowing from other languages do seem to be working, even if we are very far away from our ultimate goal. Similarly, talking again about features, you know that things like LDA, when you have labeled data, always give you better features because they focus on discriminating between categories you care about and try to suppress differences based on nuisance information. In this case, we have no category labels to work with because everything is unsupervised. So even the bootstrap works. You get some automatic units first, pretend they're your labels, do LDA or do bottleneck features, and you get something out of that. So those ideas seem to be working. One of the things that didn't work is that we wanted to borrow priors from the other languages in this classic Bayesian way, saying if there's a prior on acoustic model parameters, and if I have lots of languages on which I learn the posterior distribution on those parameters, will that somehow be a better prior for learning acoustic models in the new language? This was one of Leda's experiments that didn't work. So not everything we tried worked, of course. Going on with acoustic unit discovery, we wanted an intrinsic measure, this normalized mutual information to work with. And we always told ourselves, look, let's not get too carried away by our intrinsic measures because our end goal might be keyword spotting or topic detection. And so we did look at whether improvements in NMI also results in improvement in word spotting. So whether two examples of the same word appear similar and examples of two different words appear different. And these things track. So better NMI results in better same different word discrimination. And also better NMI results in better topic clustering or document clustering. This was Santosh's results. So those were nice results to look back at and say, oh yeah, that was a useful thing to have found this summer. Going on, if you think about the word recognition or the segmentation of acoustic units into word-like groupings, this was work that Thomas presented. And if you even go one step further and think about actually, let me talk a little bit about Mirko's work. So what Mirko did is he said, let's look at the grapheme to phoneme learning problem. And if you look at what's the state of the art right now, it is this sequitur system that people in Aachen developed some years ago. And actually, it's a pretty good system, but what it has is it has a number of these knobs which are a little annoying because you have to get them just right for it to work very well. So Mirko sort of rewrote the whole book on that and said, no, let's have just a formal Bayesian model which doesn't require a whole lot of tuning, and let's see if we can get it to work well. And in the supervised setting, as he showed in his results, it works as well as the Aachen model. So at least we have one alternative to the Aachen model which works as well. And the nice thing is it's Bayesian, so it is easy to take that into the unsupervised setting. So that was a nice contribution. And then Thomas and others, they started looking at the more end-to-end problem now, not just discovering acoustic units from bottom up, but trying to bring top-down constraints. So we have a couple of Bayesian formulations of frameworks over there using these hierarchical Pittman-Ure models. And on those, the main accomplishment in the summer has been that a lot of pieces in the pipeline have been implemented and put together. So the first results that came out of this integrated pipeline indeed have error rates like 80% and 70% and 90%, so nothing to write home about. But remember, these are completely unsupervised models with a little bit of knowledge injected here or there. So this is not too surprising for the first attempt. And I believe that because everything is now together, this allows us to do experimentation, and I think over the next few months, we should be able to get pretty far and be able to actually test this idea to see if it works. And as several people said, the current implementations are sort of still coming together. We've sort of characterized how difficult the problem is for ourselves, and we've invented things like these pruning techniques, which Daichi didn't get a chance to talk about, which becomes necessary if you're going to work with these very large FSAs. So all in all, looks like many of the pieces have come together. And as for the final goal of the team, it was a lofty goal. It still remains a goal. And we have made some clear steps in that direction. So I think it's something to be quite happy about for the summer, but to sort of remind ourselves that the real goal is still far. So we keep going. And we have a near-term deadline. We have a PI meeting coming up in a month. So we hope to wrap up some of these experiments before then. And then after that, next year, there's going to be a real evaluation of this work in a more formal sort of objective setting. So by then, these results will be mature enough to be deployed and evaluated when DARPA does its Lorelei evaluation, and I think in the June time frame next year. So let me stop there. Lukasz, is there anything you want to add? No? Anybody else from the team wants to add to this? No? Okay, so that's the end of the team presentation. And again, we are 3 minutes ahead of schedule. So we have time for questions. Okay, questions for the team? I'm just going to deflect them. I'm not going to answer any of them. So go ahead and ask. Yes? No? Anyone? No questions. Lukasz, I'm assuming that means it was a terrific presentation. All right, so thanks. Let's take a break for the... Wait, oh.
I have one question. Do you have anything better number I do. You do?
He does, okay. But he's... Okay, all right, there was a question. Yes, Heidi. Yes. Say that again? How you spell it. Oh, I see. So in other words, since you know the orthography of the language and since you know how many characters there are in the language, does it then help you figure out how many acoustic units there might be? Clusters, okay. So just grouping. So if you just looked at character sequences and groups of character sequences that appear often enough that you might want to think of them as a single unit. So does that help you come up with some sense of how many acoustic units there ought to be? So guys who worked on it, anyone wants to offer? Yes, Taka? Let me bring you the microphone, and that way people on the web can hear you.
Actually, I want to ask about the collapsed give sampling to Evo.
Oh, I think you answer Heidi's question.
Yeah.
Just let him answer first.
Yes, so that's what we are hoping for. So actually, the model which uses the grapheme to phoneme like model, it's exactly what it is trying to learn. So it assumes that we have alphabetic language, and it tries to model the phonotactics and the rules. So basically, it is some joint n-gram on sequences of letters and sequences of the acoustic units, and it tries to see the pattern, the statistical pattern in sequences of letters and sequences of acoustic units, and tries to find the pattern in that, and from that learn how we could easily merge the sequences of the acoustic units into sequences letter and then to sequences of words given the language model. So this is exactly what we are trying to learn in one of the approaches. In the Takai's approach, he tries to be blind to that, but then his approach is also useful for non-alphabetic languages, but then the task is much more difficult because you don't have this additional supervision. Right?
So, can I ask a question? Yeah. So, I'm interested in the collapse to give sampling, and I thought he said it is working, but has some need more work to apply to HMM, and I want to know what is the difficulty?
So, Ivo, the question is, can you apply the collapse give sampling to HMMs, and what is the difficulty? Give the microphone.
Honestly, I'm not 100% sure about this, but I've read papers about applying collapse give sampling to HMMs with discrete emission probabilities. So I think the problem with continuous data is, I think it's probably has to do with deriving the full conditional distribution. I guess it'll be sort of a complex distribution to derive mathematically.